So welcome everyone for this new SIPTA seminars. Today we are quite glad to have a talk by Ignacio Montes that some of you know already quite well, that will talk to us about connections between game theory and imprecise probabilities. But without further delay, I will let someone that knows Ignacio very well, or Nacho, as we call him, that is Enrique Miranda. So I will handle the scientific animations to Ike.
Okay, thank you, Sebastian. And well, welcome everyone. Thank you for being here. Well, it's my pleasure to introduce Nacho for this seminar, where he's going to be talking about the connections between imprecise probabilities and game theory. Well, Ignacio Montes, he made a PhD at the University of Oviedo. Then he was with a postdoc at the Compiègne Technical University. He was also in Universidad Carlos III in Madrid. He's been doing research stays in the University of Trieste, also in Ghent University. Well, he's touched many different topics in many different parts of imprecise probabilities. So, well, okay, I think he's a very good speaker, and it's well, very good for us that we have him here today. And well, I'm just giving the floor.
Thank you for the introduction, Ike. I have to say that Ike forgot to say that he was my supervisor. Well, I have to say that it is a pleasure to give this seminar. I want to thank the SIPTA Executive Committee for the invitation, and in particular to Sebastian. I also have to say that I spent some time thinking about the possible topic. And finally, I decided to speak about the connection between coalitional games and imprecise probabilities. And I want to pose a question from the very beginning, because I want to ask you whether imprecise probabilities and coalitional games are equivalent or not. And the aim is to be able to give an answer to this question after the seminar. And also, you will see that along the presentation, I will not only speak about the things that other people do or things that I've done in the past, but I will also propose some open problems which I think that are quite interesting. Before starting the main part of the presentation, here you can see, well, I give you some information or about where I come from. I'm an associate professor at the University of Oviedo in the north of Spain. So you can see here in the map, in the top, the red part, which is where Oviedo is. And also you can see 4 pictures, which I think that represent quite well what how Asturias is. So you can see the coast, the mountains, and also the green forests. When people think about Spain, I think that most of the people think about super good weather, sunny days, Mediterranean food, paella, or bullfights. But Asturias is a bit different, because here we have green forests because it rains a lot. And also in the summer, the temperature is not so high, and we have a particular style of food. So we are a bit different from the rest of Spain. In this seminar, I will speak about coalitional games, but I will about distortion models or approximations of lower probabilities. I have collaborated with some people in these 3 topics, in particular with Sebastian in the topic of distortion models, Paolo Vicik in the topic of approximations of lower probabilities, and also I have done some works with 2 young students who have recently finished the degree of mathematics, which are Carmen Envil and Andrés Presa. Also, in the right part of the slide, you can see some authors who have done important contributions to these 3 topics. Well, I have to say that the list is not exclusive, but I think that these are a good representative of all the authors. So, for example, we have Shapley, who proposed one of the main solutions of a coalitional game, and his solution was investigated by Philippe Smets and Didier Dubois from the point of view of belief functions and possibility measures. Also, Michel Gravis is an expert in capacities, decision-making, and the connection with coalitional games. In the topic of distortion models, Andrei Brownevich analyzed a particular type of distortion model that appears by doing a direct transformation of a probability measure, and Renato Pelesoni, Lev Utkin, and Teddy Seidenfeld analyzed some particular distortion models, such as the linear vacuums, the parimutuel, or the total variation models. And regarding approximations of lower probabilities, the original definition of outer approximation was given by Andrei Bronovich and Thomas Agustin. These approximations have been used recently by Barbara Vantaggi and Davide Petturiti in many different fields. And also they have been investigating from a slightly different point of view by Damian Escu. So after these preliminaries, we are ready to start the main part of the presentation, which is divided in two main parts. In the first part, we are going to analyze lower previsions, and we are going to investigate the connection between we are going to speak about lower probabilities and the connection with coalitional games. And in the second part, we are going to speak about a more general model, the model of lower previsions. So to start, we speak about some well notions about lower probabilities. I guess that more or less you are familiar to them. So a lower probability is a function that assigns a value in the 0-1 interval to each event. And we assume that it satisfies two properties, which are monotonicity and normalization. Also, using the conjugacy relationship, we can define an upper probability by using the equation that we have here. And there are many different ways of interpreting the lower and conjugate upper probability. For example, if we use the behavioral interpretation, which is an extension of the interpretations of probability measures given by Bruno De Finetti, the lower probability is understood as the supremum buying price that we are willing to pay for a bet on the event. And similarly, the upper probability is the infimum selling price for the bet on the event. On the other hand, we have the epistemic interpretation, where we assume that there exists a probability measure modeling the uncertainty of the experiment, but due to a number of reasons, we don't know all the values of the probability. So the best that we can do is to give lower and upper bounds for the real but unknown probability P0. And there is also another possible way of interpreting lower probabilities, which is in terms of coalitional games. And this is the interpretation that we are going to follow in this presentation. Also, when we have a lower probability, we can define a set of probability measures which contains the probabilistic information about the lower probability. This set of probabilities, which is closed and convex, and it is usually called the credal set, is defined as the probability measures which dominate the lower probability. Here, I am showing an example in a 3-element possibility space, because in this particular case, in possibility spaces with only 3 elements, we can give a quite nice graphical interpretation of the credal set. Also, in order to determine the lower probability, the values of the lower probability, we just need to focus on the lower and upper bounds or the lower and upper probabilities of the singletons, because once that we know the upper values, the upper probabilities on the singletons, we know the lower probability on the events of cardinality too. So this means that in order to determine the credal set, we only need to impose conditions on the singletons. The graphical representation is done in this triangle that we have here, which is usually called the simplex. And we interpret this triangle in the following way. Each point in the triangle is a probability measure. So for example, the vertex that we have here close to x1 is the probability measure that assigns value 1 to x1 and 0 to the others, and similarly with the other 2 vertices. Also, the point in the middle of the triangle is or represents the uniform distribution, and the closer we are to x1, the higher its probability, and so on and so on. So in order to determine the credal set, we impose conditions on the singletons. So we know that the probability of x1 belongs to the interval 0.1, 0.4. So this means that the credal set must be included between these 2 lines, because this one contains the probabilities assigning probability 0.1 to x1, and the other one, the other line, assigns probability 0.4 to x1. So the credal set is between these 2 lines. Similarly, we can also impose conditions on x2 because its probability is included between 0.3 and 0.7, and similarly to the other singleton, to x3. So at the end, for each singleton, we have a region, and in order to determine the credal set, we have to take the intersection of the 3 regions, because any probability in the credal set must satisfy the 3 conditions. So taking the intersection, we get this gray part, which is the credal set, which contains the probabilities that are compatible with the probability measure, with the lower probability, sorry. Also, I said that the credal set is closed and convex, and this means that it is characterized by the extreme points. The extreme points are the vertices of this polytope, and they are important because if we know them, we can determine the whole credal set, because any probability in the credal set is a complex combination of the extremes. When we use lower probabilities, we also impose some rationality criteria. The main ones are avoiding sure loss and coherence. We say that the lower probability avoids sure loss when the credal set is non-empty. So this means that there is at least one probability compatible with the information given by the lower probability. And it is coherent when, for any event, the lower probability can be attained in the credal set. And this property of coherence has also a graphical interpretation in the following way. If we consider the same example as in the previous slide, we have here a lower probability, which is can be easily proven that is coherent, but we can modify one of the values. For example, imagine that we modify the lower probability of the event x1, x3, so we replace 0.3 by 0.2. And consequently, using the conjugacy relationship, we also modify the upper probability of the conjugating. So the probabilities assigning probability 0.8 to x2 are those that are in this green line. But as you can see, this green line has nothing in common with the credal set. So this means that we cannot find a probability in the credal set assigning probability 0.8 to x2. So this means that we are giving an upper bound too high to the probability of x2. In order to get coherence, what we have to do is to reduce a bit the upper probability until we find a probability in the credal set assigning that value. Another property that we are going to mention is the property of monotonicity that may be satisfied by some lower probabilities. And it holds when this inequality that we have here is satisfied for any pair of events. If you take a look at this inequality, it is somehow similar to the well-known inclusion-exclusion formula for probability measures, but here we are only imposing an inequality, not an equality. The interpretation of this property is not so clear. It is more or less strange, but when the lower probability is too monotone, then there are many different practical advantages. Some of them has been summarized in this very nice paper by Sebastian de Sterke, and the main ones are the following. So if we have a too monotone lower probability, it has a unique extension to gambles, preserving to monotonicity by means of the Choquet integral. It can be characterized by means of the modulus inverse. We have simple formulas for the condition in the model by using the regular extension. And also I said that the credal set is characterized by the extreme points. And when the lower probability is too monotone, we have simple formulas for computing these extreme points. So you can see that from the practical point of view, this property has some important benefits. And even more, we are going to see along this presentation that there are also other interesting benefits of using to monotonicity. As an example of a lower probability, we can speak about distortion models. What is a distortion model? The idea is to take a probability and to create a distortion around that probability. So create the kind of a neighborhood around it. There are many ways of defining distortion models, and in particular, we are going to consider two of them. The first one is the linear vacuous, which is defined using a probability measure and a distortion factor using the expression that we have here. So we define a lower probability by reducing a bit the values of the fair probability P0 in a way that it depends on the distortion parameter. Here we have an example. We have a probability measure P0 and a distortion factor. We can define the lower probability of the linear vacuous model, and we can compute its credal set, which is this gray triangle that we have here. This is the credal set of the linear vacuous model. Similarly, we can also define the parimutuel model, which defines a lower probability by also creating a distortion, by also reducing the values of the probability P0, but using a different formula. And in this particular example, we obtain a credal set here in blue, which is also a triangle, but with a different orientation than the other one. We have seen in previous papers that both the linear vacuous and the parimutuel have kind of dual properties. And this is why these two triangles are in some way symmetric. Also, note that here I am using this terminology to denote the credal set of the linear vacuous model and the credal set of the pari-mutual model. The reason is that we are using the general notation from distortion models, because this can be interpreted as a topological ball centered in P0 with a radius delta with respect to the linear vacuous or the pari-mutual models. And in particular, I have to say that both the linear vacuous and the pari-mutual models are two monotone. So they have all the practical advantages that I have mentioned before. So after explaining these preliminaries, we are ready to start speaking about coalitional games. And the question is, what is a coalitional game? Now we have a set of players. An event is a subset of players, which is understood as a coalition of players. A coalition of players that may decide to play together in order to get a higher reward. And the game, the formal definition of a game, is a function assigning a non-negative value to each coalition. And the interpretation is the following. So if we have a coalition, the value of the game is the minimum amount of money that is warranted by the coalition if they decide to play together. And in particular, if we take the coalition formed by all the players, the value of the game is the total reward, the amount of money that we have to split among the players. At this point, we have to say that we also impose some extra conditions, but which are super reasonable. On the one hand, we assume that if we have a coalition with no players, so if we have the empty coalition, the value that we assign to this coalition is 0. And also we assume that the game is normalized. But this is not a restriction at all, because once that we know the total reward, we can always divide all the values by the total reward, so we obtain a normalized game. And the other property that we impose is that of monotonicity. And this is also a quite reasonable property, because this means that the higher the coalition, the greater the reward. But if you take a look at the definition of a coalitional game, it turns out that both normalized games and lower probabilities are the same. A normalized game is nothing but a lower probability. Okay, we are changing the notation, we are changing the interpretation and the terminology, but the mathematics behind both notions are the same. Also, we have seen some notions related to lower probabilities, and they have the counterpart in the field of coalitional game. So, for example, what we call a conjugate upper probability is called conjugate game. The rationality properties of avoiding sure loss or coherence are called balanced games and exact games. The credal set is called the core, and the interpretation of the core is that it contains the additive ways of splitting the money between the players, satisfying the requirements of the coalitions. And finally, the extra property of monotonicity is called convexity in the field of coalitional games. So if the question is, are lower probabilities and coalitional games equivalent? The answer is yes, they are. All the notions are the same. We are just changing the notation, the terminology, and the interpretation, but the mathematics behind both theories are the same. A particular example of this equivalence is the two papers that we have here in this slide. So we have a blue paper, which was published using the terminology of lower probabilities in 2007, and the gray paper that was published in 2003 using the terminology of coalitional games. But the surprising thing here is that the main result of both papers is exactly the same. So the main result says that if we have a possibility space with n elements and we have a coherent lower probability, then the credal set has at most n factorial extreme points. But using the terminology from game theory, this is equivalent to saying that if we have a game with n players, then the core has at most n factorial extreme points, which is exactly the same result. So what is the moral here? The moral here is that there are two different theories which are equivalent. So I think that what we should try to do is to build a bridge between both theories. So to be stronger, to unify both theories, to understand the connections between them. So once that we know that there is a connection between coalitional games and lower probabilities, we can try to investigate game solutions or centroids. So what is a game solution? A solution of a game is a way of dividing the total reward in a fair way. When I say that in a fair way, I refer that we should try to satisfy the requirements of all the coalitions. But using the terminology of lower probabilities, this is equivalent to finding a centroid, a point, a probability inside the credal set, in the way that we are trying to find something like in the middle of the credal set. Here we are analyzing 4 different possibilities for a solution or for a centroid of a credal set. The first one is the Shapley value, which was defined in the framework of coalitional games. But we are also analyzing the average of the extreme points, the in-center, and the contraction centroid. Here I have to say that we are going to do a couple of assumptions. So from now on, the possibility space is finite. So we have a finite number of players. And also a technical question that says that the lower probability of the proper events belongs to the open interval 0, 1. Okay, these are 2 assumptions to simplify the things. So here we have the definition of the Shapley value. So this is the amount of money that we are going to give to the player X, and we can give an interpretation of this value. So because here we are computing the difference between 2 lower probabilities. But this means this is measuring the extra benefit of the coalition when the player joins to the coalition. And we are adding a weight here, which is proportional to the size of the coalition. And at the end, we aggregate all the values for all the possible coalitions. This is the definition that is usually used of the Shapley value, but in the original paper, the definition was a bit different, because what Shapley was looking for was for a solution satisfying 4 properties, which he considered reasonable: efficiency, symmetry, linearity, and the null player property. And he proved, in the paper that we have here in the slide, that there was a unique solution satisfying these 4 properties, and the unique solution is the definition that has his name. So there is an axiomatic way of justifying the use of the Shapley value from the point of view of coalitional games, which is something super nice. Also, when the lower probability is too monotone, then the Shapley value belongs to the credal set. So it satisfies the requirements of the coalitions. But, and here it appears the main problem of the Shapley value, when the lower probability is not too monotone, then it may not belong to the credal set. And this means that if the property of true monotonicity doesn't hold, then we may be violating some of the requirements of the coalitions. And this is something quite negative, because we said at the beginning that we wanted to split the money in a fair way. We wanted to satisfy the requirements of all the coalitions. In the example that we are analyzing here, we have a coherent lower probability in a 3-element possibility space. And well, it is well known that in a 3-element possibility space, coherence means also to monotonicity. So in this particular example, the Shapley value belongs to the credal set, and we obtain this point that we have here. Okay, so we have a problem with the Shapley value because it doesn't belong to the credal set in general. So we try to solve this problem by using the average of the extreme points. So we have a coherent lower probability, and we have seen before that in this particular case, the number of extreme points is finite, is at most n factorial. So what we can do is to aggregate them to compute the average of the extreme points using the formula that we have here. So once that we know the extreme points, applying this approach is super simple. Also, by definition, we are computing a convex combination of the extreme points. So by definition, this value belongs to the credal set. So we are avoiding the problem of the Shapley value, and we are satisfying the requirements of all the coalitions. Also, even if the Shapley value and the average of the extreme points are different in general, there is a particular situation where they coincide. And the situation is if we assume true monotonicity and the credal set has exactly n factorial different extreme points. In that case, both approaches are the same. In our example, we have a credal set with 1, 2, 3, 4, and 5 extreme points. And if we average them, we obtain this red point here, which is the average of the extreme point. A third approach is based on computing an in-center. And in order to define this approach, we need a distance between probability measures. In order to consider a distance, we could consider the Euclidean distance, the Weisstein distance, or our choice here, which is the total variation distance. This distance measures the maximum absolute difference between the two probabilities. And once that we have a distance between probabilities, what we can do is to define a topological ball. So we can select a probability measure and create a ball around that probability with a given radius with respect to the total variation distance. And what we want to do is to insert one of these balls inside the credal set, but at the same time using the largest possible radius. So we want to put the largest possible ball inside the credal set. So this largest possible radius is what we call here the in-center radius. And once that we know the center radius, we call in-center to any of the possible centers of the balls that we insert in the credal set with a given in-center radius. The main properties of this approach is that it exists whenever the interior of the credal set is non-empty. It may not be unique, which is something negative, because we are looking for the solution of a game, and here we may obtain more than one solution. And also, by definition, this in-center belongs to the credal set. So again, we are avoiding the problem of the Shapley value. In our particular example, you can see here in red one of the in-centers, and in gray, in dark gray, you can see here the ball induced by the total variation distance center in this in-center. So in particular, you can see that in a 3-element possibility space, the total variation distance induces an hexagon inside the credal set. But in this case, the solution is not unique because we can find another ball with the same radius that is also inserted in the credal set. So we have two different in-centers. But indeed, in this particular case, there are not only two different in-centers, there are infinitely many, because all the red points in the segment are in-centers. So this is a problem because we may find infinite solutions. And in order to avoid this problem, we propose a different approach, which is based on a contraction approach. This fourth method has more difficult definition from the mathematical point of view, so I prefer starting with the example. Here we have a credal set with 5 extreme points, which is determined by 5 segments, as we can see here. So the idea of the contraction approach is to contract the credal set in a uniform way in all the directions. So we want to obtain a credal set with the same shape, but a bit smaller. And how can we do that? The idea is that we will increase the upper probability in all the events in the same quantity, and at the same time, we reduce the upper probability in the same quantity. So for example, if we increase the lower probability in 0.01 and we decrease the upper probability in the same quantity, we obtain a credal set which is a bit smaller, but with exactly the same shape. But instead of considering this value, we can consider a value a bit greater. So the contraction gives a credal set a bit smaller, and we can iterate the procedure until we get something whose shape is quite different. For example, when we use a value of 0.075, we obtain a credal set which is a segment. So the shape is quite different. And this means that there was an event where the lower probability and the upper probability at the beginning were different, but after applying the contraction, this lower and upper probability coincide. So this means that for this event, we cannot contract the value more, but we can continue contracting the values of the lower and upper probabilities for the other events. So at the end, iterating the procedure, we obtain different credal sets which are decreasing, and at the end, the procedure gives a singleton, a unique point, which is what we call the contraction-Centroid. So how can we mathematically formalize this? Here we have the mathematical formulation. So what we are going to do is to split the events in 2 different parts. On the one hand, in the blue part, we have the events where the lower and upper probability coincide. And on the other hand, we have the green events, which are the ones in which the lower probability and the upper probability are different. So the events in which there is imprecision. So what we're going to do here is to contract the credal set in a factor alpha such that we keep the values of the lower probability constant for the events where the lower and upper probability coincide, and for those events in which there is imprecision, we increase the lower probability in a factor alpha. So in particular, when we do this contraction, we look for the largest possible contraction that we can do so that the set of probabilities that we obtain is non-empty. Once that we have this value and we have the contracted credal set, we can take lower envelopes and we obtain another coherent lower probability, what we call here lower P1. And the property of this new lower probability is that the number of events with imprecision is decreasing. So this means that we can iterate the procedure, and after a finite number of steps, what we get is a chain of decreasing credal sets which end in a singleton, and the element in the singleton is what we call the contraction centroid. The main properties of this approach are the following. So first of all, it is well defined, and when I say well defined, I mean that the supremum that we have here exists. It is a maximum, so we can obtain this value. Another property is that the value alpha 1, this largest possible contraction value, can be given in a super nice and elegant formula when the lower probability is to monotone. So here again, we have another advantage of using to monotonicity. And also there is a super nice property which relates the in-center with respect to the total variation distance and the contraction approach. Because we have the credal set and we can compute the set of in-centers. But also we can do the first step in the contraction centroid and we obtain a set of probability measures. So both approaches, the set of in-centers and the first step in the contraction approach, give rise to the same set of probability measures. So this means that we can understand this contraction approach as a refinement of the in-center approach, in which we try to avoid the problem of the non-uniqueness of the in-center. In the example that we are analyzing here, the process finishes in only 2 steps. In the first step, as we have said, we obtain the set of in-centers, and in the second step, we obtain the contraction centroid, which is the blue point that we have in the middle of the credal set. So far we have investigated 4 ways of defining a solution of the game or a centroid, a probability measure representative of the credal set. As a summary, we can see here in red all the set of in-centers, and in the middle we obtain the contraction centroid, which, as we have seen, is in particular one of the in-centers. But the contraction centroid, the average of the extreme points, and the Shapley value are different solutions. So in general, they don't coincide. So here I propose the first open problem. We have seen that the Shapley value is a solution that has been characterized from the point of view of coalitional game. So it is the only solution satisfying 4 desirable properties. The question is, can we give an axiomatic justification of the in-center, the contraction approach, and the average of the extreme points? This would be super nice, because if we are able to do this axiomatic justification, then we can justify the use of these other centroids as game solutions. One of the approaches that we have seen to define a centroid was based on the in-center with respect to the total variation distance. But this approach is similarly, or can be seen as a way of doing an inner approximation. What is an inner approximation? We have a lower probability, and we want to replace the lower probability by another lower probability which is a bit more informative. A bit more informative in the sense that the credal set is a bit smaller. Also, in general, what we want is to replace the initial model by another one with better properties, like for example with the property of monotonicity, but being as close as possible to the initial one. And this gives rise to the notion of a non-dominating inner approximation in a family of lower probabilities. We say that the inner approximation is non-dominating in a family when, in some sense, it is maximal. So we cannot find another inner approximation in the same family between the initial model and the transformed one. So in particular, this class of lower probabilities may be the class of two monotone lower probabilities, or we can consider also distortion models. So in particular, we can look for a non-dominating inner approximation in terms of a linear vacuous model or in terms of a pari-mutual model. In particular, imagine that we look for a linear vacuous model that it inner approximates the lower probability. So this means that we are looking for a linear vacuous model whose credal set is inserted inside the credal set, the initial one. And in particular, we may look for the linear vacuous model inside the credal set with the largest possible distortion factor. And this is what we can call here in the slide the linear vacuous in center radius. And once that we know this largest possible distortional value, we can call in center to any of the centers for which we can define the linear vacuous inside the initial credal set. So with this approach, what we can do is to define an in-center with respect to the linear vacuous model, but at the same time, we obtain a non-dominating inner approximation in terms of a linear vacuous model. So at the end, it is equivalent to look for a non-dominating inner approximation as a linear vacuous model and looking for an in-center with respect to this same model. The main properties of this approach is that we know when this solution exists. It may not be unique when it exists. And also, again, under two monotonicity, we have a simple expression for computing the largest possible distortion parameter, what we call here the linear vacuous in center radius. For the example that we are analyzing, we can find infinitely many in-centers with respect to the linear vacuous. Here in the figure, I am showing two of them because these two red points induce linear vacuous models with the largest possible distortion factor, which in this case is 0.15. And you can see that both are inserted inside the credal set. A similar approach, exactly the same approach, can be done when considering the pari-mutual model. So in this case, we want to insert a pari-mutual model inside the credal set with the largest possible distortion parameter. And in this way, we obtain an in-center with respect to this model, which is also equivalent to looking for a non-dominating inner approximation as a pari-mutual model with the largest possible distortion parameter. The properties are exactly the same as for the linear vacuous model, exactly the same. But in this particular case, for the example that we are analyzing here, we obtain, for this particular example, a unique solution in terms of pari-mutual. So the centroid that we obtain is this red point here, and the credal set is the triangle that we can see here, which, as I said, in this case is unique. So you can see that when we speak about in-centers, we can use the total variation distance, any other distance, but also distortion models. In this case, we are considering the linear vacuous of the pari-mutual model, but exactly the same philosophy can be followed, can be done with other models such as I don't know, the L1 distance or the Kullback-Leibler divergence. So another question is, okay, we are defining a game solution or a centroid using the linear vacuous and the pari-mutual model, but do they make sense from the point of view of coalitional games? Can we give an axiomatic definition or an axiomatic justification of this approach? I think that it could be super nice if we can get something like that. Well, in this first part of the presentation, the conclusion is that lower probabilities and coalitional games are the same. They are equivalent. But the question that I proposed at the very beginning of the presentation was a bit more general, because what I asked was, are imprecise probability models and coalitional games equivalent or not? And in order to try to solve this question, we are going to speak about a more general model, which is that of lower previsions. And for this aim, let us consider a simple example. Imagine that we have a game with 3 players, and we have here the conditions imposed by the players. So the first player wants at least 10% of the total reward. The second player wants the 20% of the reward. If player 1 and 2 play together, they want together at least 40% of the reward. And the other condition that we have is that the third player, she says that she's not going to impose a minimum reward, but she says that she's a player as strong as the first one. So what she says is, I want as much money as the first player. And these are the 4 conditions that we have. If we try to use a game or a lower probability to model this information, the first, second, and third conditions can be easily given, just the value of the game in one coalition with the given value. But the problem is what happens with the fourth condition. Because in the fourth condition, we are not giving a minimum value for a given coalition. Instead, what we are doing there is to compare the final reward of 2 different players. And this is some information that cannot be modeled by a lower probability or by a coalitional game. We can give a graphical interpretation again of this game. So for example, here we have the condition, the first condition of the first player, the condition of the second player, of the coalition of the first and second players, and the condition, the fourth condition, which is the difficult one, the condition that we cannot model by using a game. So we want that the probability of the third player to be greater than or equal to the probability of the first one. And this corresponds to the red region that we have here. Why? The reason is that the red dashed line that we have here is at the same distance from x1 and x3. And this means that this red line contains the probabilities assigning the same probability to the 2 elements. But in particular, we want those probabilities assigning more probability to x3 than to x1. So we want to take the part that is closer to x3. So this is the region that satisfies the fourth condition, but this region cannot be obtained using a game. The reason is that graphically, we have seen that a game or a lower probability put conditions that are segments parallel to the borders of the triangle. And of course, the line that we have here is not parallel to any of the borders. If we take the intersection of the 4 regions, we obtain what should be the core of the game, which is the set of payments which are compatible with the 4 conditions. But as I said before, this set of payments cannot be obtained by a game. Also, once that we have this set of payments, if we take lower and upper envelopes to know which are the minimum and maximum reward for each of the players, we obtain, we put this red, green, and blue lines, and we obtain one part here, the dark blue, the darker gray part, which satisfies the minimum and maximum requirements of any of the players, but which is not compatible with the fourth condition. So it is not an admissible way of splitting the total reward. So the conclusion is that this game, with only 3 players and 4 conditions, cannot be modeled by using a game. So what can we do in this case? We can use a lower prevision. So here in the slide, we have the basic definitions about lower previsions. A gamble is a bounded random variable. A lower prevision is a function assigning a real value to each gamble. And from the lower prevision, we can define an upper prevision using the conjugacy relationship that we have here, which is kind of an extension of the conjugacy relationship between lower and upper probabilities. And also, from the lower prevision, we can define a set of probability measures, a closed and convex set of probability measures, also called credal set, which contains the probability measures which dominate the lower prevision for any gamble. And here we are interpreted the probability of the gamble as the prevision of the gamble or the expectation of the gamble with respect to the probability. Also, we can define the rationality criteria of avoiding sure loss when the credal set is non-empty, and the property of coherence when the lower prevision is the lower envelope of the credal set. The nice thing of using coherent lower previsions is that coherent lower previsions and credal sets are 2 different models, but which are in one-to-one correspondence. So if we have a coherent lower prevision, we can define the credal set, And when we have the credal set, we take lower envelopes and we obtain again the same coherent lower prevision. So it doesn't matter which model we use because we are modeling the same information. But both models, which are equivalent, are much more informative than coherent lower probabilities. The reason is that once that we have the coherent lower prevision or the credal set, we can define the restriction to events using the formula that we have here. So the lower probability of an event is the lower prevision of the indicator. In this way, we obtain a coherent lower probability, but different coherent lower previsions or different credal sets may induce the same coherent lower probability. So this means that using coherent lower probabilities or credal sets, we can capture more information. We can model more properties than only using coherent lower probabilities. In particular, in the example that we are showing here, we can model the information using a coherent lower prevision. So for the first, second, and third conditions, we only define the lower prevision of the indicator of the events and we assign the value. This is super simple. The problem was with the fourth condition, and here what we can say is that the lower prevision of the difference of the indicators is 0. And this means that any probability in the credal set will assign more probability to x3 than to x1, which is exactly the kind of property that we want to model. And in particular, if we compute the credal set associated with this lower prevision, we obtain what we call the core before, what we said that was the set of payments which were compatible with the conditions given by the players. So the moral here is that even if lower probabilities and coalitional games are equivalent, lower previsions are much more powerful. They allow to capture information that coalitional games cannot model. So, coming back to the initial question of this seminar, are IP models and coalitional games equivalent? No, they are not, because in the imprecise probability theory, we can find tools which are more powerful that allow to capture more information than coalitional games. This is like the final conclusion. But at this point, someone may say, okay, so you are using lower previsions for modeling the information, but for example, can you speak about the game solutions as you did for the case of games or lower probabilities? The answer is yes. We can define the 4 centroids for the 4 game solutions in a quite similar way. So for example, with respect to the Shapley value, we have the coherent lower prevision or its equivalent representation in terms of a credal set. We can compute its restriction to events, so its coherent lower probability, and we can compute the Shapley value. So for example, in the example that we are analyzing in this part, we have the credal set. We can compute the restriction to events, and when that we have the coherent lower probability, we compute the Shapley value, which is the red point that we have here. Of course, we have again the same problem as the Shapley value for lower probabilities. It may not belong to the credal set. But here I propose another open problem which I find really, really interesting. The Shapley value is characterized from the point of view of coalitional games as the unique solution satisfying the properties of efficiency, linearity, symmetry, and null player properties. But these 4 properties are given in terms of coalitions, are given in terms of events. So I guess that in some way we can rewrite these 4 properties using gambles, and I guess that there should be a way of giving a Shapley value for lower previsions, but not only for lower probabilities, in a way that is more natural than just taking the coherent lower prevision, computing the restriction to events, and then computing the Shapley value. So I think that this is a super interesting problem. With respect to the average of the extreme points, if we have a credal set which is a polytope, so a credal set with a finite number of extreme points, then the definition of the average of the extreme points is exactly the same. So we compute the average of all the extreme points. In the example that we are analyzing, we have only 4 extreme points, and If we aggregate them, we obtain the rate point that we can see in the figure. The definition of the in-center radius with respect to the total variation distance is also straightforward, because the idea is the same. We want to put a ball according to the total variation distance inside the credal set with the largest possible radius. So the definition is exactly the same as we saw before. In our particular example, we obtain a unique solution, even if in general the solution is not unique. In this case, it is. The solution is the red point that we have here, and again, we can see the hexagon, which is the ball induced by the total variation distance, which is inserted inside the credal set. And finally, we can also speak about the contraction-Centroid, whose idea is exactly the same. I will skip the maths here because they are a bit more involved than in the case of lower probabilities, but the idea is the same. So we have a credal set determined by 4 segments, and we want to contract it uniformly in all the directions so that we obtain a credal set that is a bit smaller but with the same shape. So for example, doing a small contraction, we obtain this second credal set, which is a bit smaller. And doing a further contraction, we obtain a credal set whose shape is a bit different because now we only have 3 extreme points. So this means that at some point there was a gamble where there was imprecision, but after doing the contraction, the lower and upper previsions coincide. So we continue the contraction approach in other gambles where there is imprecision. So after a finite number of steps, we get a chain of decreasing credal sets ending in a singleton, which is what we call the contraction-Centroid. So you can see that we can define it in a quite similar way. As a summary, we can see the 4 centroids for this particular case, and in particular, we can see that the 4 of them are different solutions or different centroids of the credal set. But again, we have another open problem, because for defining the average of the extreme points and also for defining the contraction-Centroid, we need the credal set to be a polytope. Because if it is not a polytope, then it may have an infinite number of extreme points, and in that case, we cannot compute the extreme of the average point, so we need to find something alternative. And in the case of the contraction-Centroid, everything is more involved, so I am not sure whether the process of contracting the credal set would end in a finite number of steps. So I think that this is something that deserves some attention. So with this, we are arriving to the end of the presentation, and here we have the main conclusions. If we wonder whether lower probabilities and coalitional games are equivalent, the answer is yes, they are. The only difference between them is the notation, the terminology and the interpretation, but the mathematical notions are the same. So what I think that we should do is to try to build a bridge between both theories and to try to work together, because at the end we are doing the same. As we saw before, it makes no sense that in 2 different papers we are proving the same but with different terminology. It makes absolutely no sense. So we try to clarify the connections between both theories. But if the question is, are IP models equivalent to coalitional games? The answer is no. In the IP theory, we can find models which are much more powerful, which are more informative than lower probabilities or coalitional games, such as, for example, lower previsions that allow to capture more information than coalitional games. So the answer is no. Imprecise probability models are more general, more informative. But at this point, I have my final open problem. We have seen that we can use coherent lower previsions to model information about games, but we know that there are also other models within the IP theory which are as general as coherent lower previsions. We can also use, for example, set of desirable gambles, or we can use choice functions or any other model. So the question is, are coalitional games connected to these other models, such as, for example, set of desirable gambles? Or even more, can we express a game solution in terms of a set of desirable gambles, for example? I think that these are quite nice problems, solving these problems or analyzing them, I think that will help us to understand the connection between coalitional games and other models within the imprecise probability theory. And just to conclude, let me show you some references, 4 references of the results that I have shown you along this presentation. The first paper is a paper that I published with Enrique Miranda in 2018, where we analyzed the Shapley value and also other solution, other game solution, which is the Banzhaf value, from the point of view of lower probabilities. The second paper is a paper that is currently under review, and it's the paper where we analyze the 4 game solutions that I have proposed here, and where we also use these centroids to define a kind of measure of centrality in a credal set, or a measure of agreement in a solution in coalitional games. Also, I have been speaking about distortion models, and here you have 2 papers that I published also with Enrique Miranda and Sebastian de Sterken. And finally, with respect to inner approximations, here we have the tentative title of a paper that we are currently preparing in collaboration with Andres Presa. And that is all what I wanted to say. I just want to say that I don't know if you agree or not with me that IP models are a bit more general than coalitional games, but either if you agree with me or not, it would be super nice to be able to discuss it face-to-face in the next SIPTA conference that will be held here in Oviedo next July. And that's all. Thank you for your attention.